All right, next we're going to go a little deeper into down into Earth and talk about plutonic intrusive igneous bodies. Remember, plutonic bodies are those that are a little bit deeper in Earth's surface. The first one we're going to talk about is the lopolith. These names are great, right? I love them. So a lopolith is a large saucer-shaped intrusion. You can think of it kind of like an upside-down laccolith, right? If a laccolith was a domed-up sill, a lopolith is a saucer-shaped intrusion. So what processes do you think might form the lopolith? It makes sense that a laccolith pushes up because magma is lower density than the rock around it. It wants to rise. But what might cause that saucer shape, right? The magma isn't pushing down. So how does it get that downward shape? Well, this is actually pretty cool. There's a few different ways that we think these can form, but one of the most common ways is through meteorite impacts. So for example, there's a lopolith up in Ontario, Canada, that we think was triggered by the impact of a large meteorite. And we think this because you can actually see impact debris on the roof of the lopolith, which makes us think that it was formed by a meteorite explosion crater. Right, the next plutonic igneous body we're going to talk about is a batholith. Batholith, as you can see in this figure, that's that pink balloon shape feature. There are large bodies of granitic rock that extend considerable depths into the crust. So these batholiths are huge. They can have huge exposures on Earth's surface if they are exposed on Earth's surface, exceeding 100 square kilometers. If they're smaller than this, they're often called plutons or stocks. So for example, Stone Mountain in Georgia is a pluton. You can think of it like a small batholith, whereas the Sierra Nevada mountains and much of California is a batholith, right? It's huge. So batholiths are always composed of rocks that we refer to as granitic in the broadest sense of the word, right? It's not always granite, but it is the more felsic crustal rock, so granitic. And isotopic studies have shown us that batholiths often derive by melting continental crust, right? Makes sense if they melt continental crust, that's why they form granitic batholiths. But some of them can be derived from deeper magma down from the mantle. So just to show you how large these things are, this is an image taken from a satellite. So you can see, right, this is a huge scale. It's a NASA photograph, and these giant white blobs, that's the top of the batholith we're actually seeing exposed on Earth's surface. So how do you think these batholiths are formed, right? Where do we get that like weird balloon shape of granite in our crust? And hopefully that balloon shape gave it away for you. This is formed by basically rising plumes of low density magma, right? So the overall shape is considered to be caused by, or much like a diapir. So in other classes, you might have heard of salt diapirs. This is when salt or halite beneath the surface rises up in this dome-like shape because that halite is less dense than the rock around it. Well, magma can do that as well, right? So this diapir buoyantly rises upward through the lower part of the crust, which is kind of plastic, flows, not quite flows, but is a little mushier than the rock at the surface, a little easier to bend. And then when it gets into the upper brittle crust, it mushrooms out, right? Creating that large balloon shape. So in this image, it's showing honey rising up through oil to imitate the batholith, or the magma that creates the batholith, rising up through the continental crust.